Hi everyone, my name is Adil Abdu, and this is my creative assignment 2 for dynamics, where I'll be going over a lecture related to dynamics. The main topic of this lecture will be about the three dimensions of rotation on an aircraft. So for an aircraft, there are three axes on which it can rotate, the X, Y, and Z, or more commonly denoted the roll axis, the pitch axis, and the yaw axis. So all bodies in a 3D frame, unless having their movement fixed, are able to move also or rotate in three dimensions. This does not just apply to airplanes, but for planes specifically, we denote it as pitch, roll, and yaw axes. The production of rotation. So the three moments that produce rotation are pitching, yawing, and rolling, as we saw in the previous slide. And what produces these rotations about these axes are what we call control surfaces. So for pitch, that control surface would be elevators. For roll, those control surfaces would be ailerons. And then for yaw, it would be rudder and a combination of ailerons as well. So we'll go through cases for each one. So for pitch, for example, if we wanted to produce a counterclockwise rotation about that pitch axis, which goes right through the center of this plane, kind of coming out of the screen towards you. So we want to produce that pitch. The elevator would deflect upwards like this. And as the airflow hits it, it produces a lift force which tilts the back of the plane down, the front of the plane up, as we see in these two arrows here. And that produces a counterclockwise rotation about that pitch axis, okay? So ailerons for roll, it's pretty much the same thing. We have that face of that aileron, as we can see right here, the air is hitting it. So for this top face, the air is hitting the top surface of the aileron, so it's pushing that wing down. And then the opposite for this aileron is pushing that wing up because it's hitting the bottom face. This again produces that clockwise moment about the roll axis. Same for over here, clockwise moment, my mistake. And then for the last one, for yaw, same thing, that rudder deflection combined with the aileron deflection. So the rudder is facing this way, air is hitting it, causing the back of the plane to come out of the screen, front of the plane to go into the screen. And if you're looking from a top side down view, that is a counterclockwise rotation, like that. Okay. So we see here that these three control surfaces all produce rotations about their respective axes. We've seen how rotation is produced along each axis, being pitch, roll, and yaw. We will see how this applies to real-world scenarios. So angular velocity in the real world. So, for example, if you have an airplane and we want to find the angular velocity of a certain point on that airplane, we have the addition theorem here, which will help us do so. So the angular, here's the theorem. The angular velocity of this body B, the airplane, with respect to some inertial reference frame A is equal to the angular velocity of said body in C, and then the angular velocity of that reference frame C in the inertial reference frame A. So we have two example problems we'll do that will show how this is useful. Here's our first example. So if we have our plane B with its reference frame of B, and we have an inertial reference frame of just Z, Y, and X, we say in this scenario that there is no rotation currently and the plane is just moving forward with some velocity, right? It's not accelerating at all, no linear acceleration, no angular velocity, just linear velocity. And at any point we see, or at this point we see that this inertial reference frame B is the same as the regular reference frame. And because of this, if we see that at any point there is rotation along one axis, then there's also rotation along that same axis in the other reference frame. So let's say, for example, this plane started rolling. So that wing goes up, this one goes down, and it has a clockwise rotation around the B2 axis. Well, as long as it isn't rotating along the B3 or B1, it's still in that same reference frame of B2 as well as Y. So it's still rotating about the Y axis for the B2, so it's equal. Now the same goes if it was to rotate, if it was to, instead of rolling, it was to pitch, so it's rotating about the B1 axis, so this drops, this goes up. The same applies for the X axis. It's still in that reference frame. Now what gets complicated is when it starts rotating in two directions at the same time. So we'll see that in the next problem. Okay, so for our next example problem, we see that we have our frame B now shifted by an angle theta. So it is pitched upwards because you see it's rotated around that B1 axis like this, going upward. So it's shifted by an angle theta from our inertial frame here. So B2 is shifted by theta from Y, B3 is shifted by theta from Z. So with the little problem we're going to do here, we're going to have two angular velocities attributed to our plane. So we're going to have one in the B3 direction, so we'll call it omega 1, and we'll call it in the counterclockwise direction for the ease of the problem, and then omega 2 in the counterclockwise direction as well, but this time it'll be around the B2 axis instead of the B3. So we have those two there. And so we have these in the B reference frame, but we want them in the A reference frame. So we'll write out our addition theorem. So W, B, and A. We'll do B1 first. So if we want to find, we'll do omega 1 first. So we want to find omega 1 in the B reference frame instead in the A reference frame. So to do this, it's a lot of trig rules. So we have here that angle theta. We see the sine theta, that opposite. If we multiply it by our omega 1, our hypotenuse, we'll find the opposite side, which is here in the y direction right there. And because it's counterclockwise, it is positive, so we see it is positive W1 sine of theta in the y hat direction. We can use the same reasoning for cosine to find it in the z hat direction. So W plus W1, it's also positive because it's counterclockwise, cosine theta in the z hat direction. So there we have omega 1 in the A reference frame. We have it there. Then we can repeat the same steps for omega 2. If we do this, same thing, omega 2 of B in A is equal to omega 2. For the sine, we see that it is in the z hat direction, so omega 2 sine theta z hat plus omega 2 cosine theta. This time it is in the y direction. So there we have that. And so because these are both angular velocities of the same body, to find the total angular velocity in the A reference frame, we add these two up. So then, I'll show the work down here. Omega t for total of B in A is equal to omega 1 sine theta plus omega 2 cosine theta y hat plus omega 1 cosine theta plus omega 2 sine theta z hat. And so there we have it. We have the angular velocity of our body. Instead of being in that B reference frame, we now have it in the A reference frame. So through this lecture, we found that angular velocity on a plane is created through controlled surfaces such as ailerons, rudders, or elevators. And these angular velocities can be found through addition theorem. And we've seen two problems, but there are many more you can create through this, and the usefulness of this addition theorem is great because you can use it to solve actual real-world problems. Thank you.